Welcome to the quickest, dirtiest thermochemistry lab ever. And so, what we're going to do is measure the amount of joules, the number of joules released by combustion of a little snappy, delicious little pretzel thingy. And we're actually not going to do that. We're going to do a really, really bad job of that. Conceptually, we're going to do it just as a food scientist would in order to work out the energy content of this food. But we're going to fail because our apparatus is so devastatingly inefficient. We're going to lose a whole lot of the energy. But let's have a look what we're going to do, because you're going to have to work out the amount of energy that goes into some water, because we're going to use this to heat up some water. We can't measure the number of joules that are stored as chemical potential energy in this directly. We have to do it indirectly by using a calorimeter. And a calorimeter, basically, it measures, well, Q equals M times C times change in temperature. M is the mass of something, and here is the something, and here is its mass. So, this is water, and, whoops, sorry, I put that down to the bottom of the meniscus, and it's 50 milliliters of water. So that gives us the mass of the water. 50 milliliters is a volume, but water is defined as being 1 gram per centimeter cubed. And 1 centimeter cubed is the same volume as 1 milliliter. So there's 50 grams of water. And we're going to place that into our calorimeter. And here is our calorimeter. It's a test tube. Well, a boiling tube to be precise. It's a bit thicker. And we put that 50 grams of water into here. So, we're going to light the pretzel using the flame. We're going to use the burning pretzel to heat up the water, and then Q, number of joules, equals M, 50 grams, times C, that's the specific heat capacity of water. If you don't know that, look it up. By the end of this unit you will know it because you use it so often. And then times change in temperature. So in order to work out the change in temperature, we need a thermometer. And I put the thermometer in there, and it's 24.8. 24.8 is our initial temperature. And now we're going to do the ticklish bit, the difficult bit, the nasty bit, the bit where it shows how bad a scientist I am. First thing, I light the pretzel. I'm losing energy already, but it's not alight yet. Yep, I'm losing energy. It's pathetic. How can I be doing such a bad job? Oh, look at that. That was hopeless. Here we go. That's burning now, and we can start to heat up the water in here. Is all the energy of the pretzel going to heat up the water? Of course it's not. We're losing masses of energy. I might set off the fire alarm any minute too. This is dreadful. But yeah, some of this energy is going towards heating up the water. So you can see kind of how one of these calorimeters works. It burns the food, uses the food to heat up a known mass of water, and then measures the temperature change, 36.7, 36.9, 37, 37.3, 37.5, 6, and it looks like it's stable at 37.6, and now it's starting to go down as that water begins to lose heat energy to the cooler environment. So you now have M, 50 grams of water. You have C, look that up, specific heat capacity of water. And you have the temperature change, the final temperature that we just had, minus the initial temperature. And then we can work out the amount of heat energy from the burning pretzel that went into the water. Obviously, the water was losing energy all the time. And then have a look at the worksheet. You're going to have to do something to design a calorimeter that works a whole lot more efficiently than what we just did. Because what we just did wasn't very good.